Hello, everybody. So let's start this morning session. The first talk of this morning is given by Professor Ci Li from Rutgers University. The title of his talk is Recent Progress on the Yao-Tian-Donaldson Conjecture.
Okay, can you hear me?
Yes, we can.
Okay, great. Thank you very much for the introduction. Thanks for the organizer for inviting me to participate in this conference in honor of Tian's birthday. I'm sorry to not be able to come in person, but I want to thank Professor Tian for all his support during my career and wish him that for his 65th birthday. So it's clear that I have been working in his field through my research career and especially on this canonical metrics on Kähler metric on Kähler manifolds, and my talk will be mostly a summary of some results about this conjecture, and also it will show that how Tian's idea has basically created this field and guided the people doing research in this direction, and I sometimes I feel that I haven't reached the Tian's expectation, even though I have been working hard in this area for many years. So I wish I could pull more significant results in future to celebrate his future birthdays conferences. Okay, so anyway, so let me start. So I will start with this uniformization theorem, which says each Riemann surfaces admits canonical kinematrics of constant curvature. So the basic principle is to try to generalize this to higher dimensions, right? So we work with the Kähler manifold. So let X be a complex manifold with a Kähler form. And the Kähler form is closed, so it defines a Kähler class. So it's a positive homology class. So by the DD bar lemma, we know that any Kähler form in the same cohomology class differs from a reference Kähler metric by a DD bar of some potential function called the Kähler potentials. So in this talk, we'll mostly consider the case one, this Kähler class is a integral class. So in this case, it's a this Kähler form represents the first Chern class of this line bundle L. Okay, so let me recall this constant scalar curvature Kähler matrix. So the scalar curvature of this Kähler metric can be written in this expression. So basically, we want to contract the ridge curvature with the metric, right? So the inverse of the metric contracted with the complex the complex fraction of this log determinant would give a scalar curvature. And the CSEK equation is the fourth. It's a fourth order highly nonlinear equation, which just says that this scalar curvature is constant. This constant actually is given by some topological intersection numbers. So it's a priori determined. So there's some special cases which make this equation simpler, which is the Kähler-Einstein case when this L, this line bundle is the first Chern class or the negative of first Chern class. So in this case, the constant scalar curvature Kähler metric equation is reduced to Kähler-Einstein equation. And if you write in terms of Kähler potentials, it becomes a complex Monge-Rampa equation. So one particular case is the final case, which means that the first Chern class is positive. So in this case, probably from the analytic point of view, it's the most interesting case. So that's because in this case, there are obstructions to the existence of K-star matrix. So the classical obstruction is the vanishing of Flack invariant. And we know actually the complete obstruction comes from this K stability. Okay, so before talking about this K stability, let me recall this Tian's properties conjecture, which give an analytic criterion to the existence of CSK metric, right? So this conjecture says there exists a CSK metric in this scalar class if and only if the K energy, which I denoted by M, is proper. Means that there exists two positive constants such that this K energy is basically sometimes called coercive. So for any K potential, we have this K energy is bounded by delta times some norm, which I just roughly denoted by the norm of phi. Actually, it's kind of a Dirichlet energy type norm, but in a Kähler set, in a higher dimensional Kähler set. We don't need the precise definition. So this properness, so this conjecture has been established. But it's a collection of many people's work. So for necessary, to prove this properness as a necessary condition, this starts with the Tian's work in 1997, I guess. And then it is refined and proved in more generality by Tian Zhu and Feng Song-Stern-Weinkauf and Davash Rubinstein in full generality. And for general polarizations, there's a work by Berman, Davash, and Lu who prove this properties. And as a sufficient condition, which means that if this K energy is proper, then there exists a K-star metric. This was proved by Tian in the final case. And then there's a big gap until more recently, it was proved by Chen and Chen for general polarizations. But the general idea, I think, which was initiated by Tian, is to use this properties property to establish some a priori estimate, especially the C0 estimate. So this has been proved in full generality. Okay, so next I want to just recall this Yaodian-Donaldson conjecture, which says that the polarized manifold XL admits a CSK metric in the first-term class of L, if and only if this XL is K polystable. So the K stability was first introduced by Tian and later generalized by Donaldson. So this is an algebraic condition, which I will discuss more later. But let me just recall some results. So K stability as a necessary condition, this is known to be true. So again, so it starts with Tian's paper in 1997. And then again, it's refined and generalized to more general settings. So by Stopa, so Stopa proved the K stability for CSK matrix with discrete automorphism group, and Berman proved the K polystability for final varieties with the automorphism group, and then Berman Davash proved the polarized case, general polarized case. So I should also mention that there is a variation of this notion of K stability introduced by Tian called CM stability. There's another version called Stability for Pairs by Jean-Paul, Tian's former student. So these are also being studied, and actually the relations with K-stability, which I will use, is still not very clear. Okay, so K-stability, as I said, so yeah, so we know that it's a necessary condition. So the typical direction now is the sufficient condition part. So this is solved now. In the final case, now there are actually several methods. The classical one was again initiated by Tian's work. So he proposed this key technical result called partial Caesar estimates in order to establish this K-stability as a sufficient condition, and also it is by starting this conjecture that many tools are being developed and used to attack this question. So in the end, so it is completed by Tian, and then Chen Dongsen Sun, and also other people. But the key idea, of course, come from Tian's work about these partial Caesar estimates and Cheeger coding Tian regularity. So this is the first type of method, and then very recently there's a very nice strategy to prove this sufficient condition by so it's initiated by Rubinstein, Tian, and Zhang, and then it's completed by Zhang, Kowei Zhang. Yeah. Rubinstein is Tian's student, was Tian's former student, and Zhang was Rubinstein's student, former student. So in this strategy, so Tian's very earlier result about the approximation by Bergman matrix is the key ingredient in this approach. And then there's a non-Archimedean method proposed by Berman, Buxom, Yongsen, and then further developed by myself, Hisamoto. And then there's also algebraic deep result by Liu, Xu, and Zhuang, who complete the circle and prove this as a sufficient condition. And also in the singular final case, we can also prove this conjecture. So this is a joint work with Tian and Feng Wang. Again, so we use some algebraic. So to complete this story, we need to use the result by Liu, Xu, and Zhuang, which I'm sure you will hear about tomorrow in Chen Yang's talk. Okay, so this is final case. And then the general polarization, this is still open. So I think now we only have this weak version where we use uniform K-stability, which is much stronger K-stability condition than the Euro K-stability. But in the end, we think it is equivalent. It should be equivalent as in the final case. But this is still open. Okay, so I want to say something more about K-stability, the definition and some of the properties about it. So then we need to talk about this test configuration, which is C-star equivalent family of polarized manifold such that so it's fibered over C and away from the central fiber. It's isomorphic to the original polarized manifold. So only over the center, the 0 point, we can get different varieties with possibly bad singularities. So it's kind of a degeneration of a smooth manifold to a single, possibly singular projective variety. And for any such test configuration, we can define TNCM weight. It's a generalized version of that invariant. So it can be calculated as some intersection numbers of this relative canonical divisor with this curly L. This curly L is an ample Q line bundle over the total space of the degeneration. So this formula was first written down in Tian's work, and then later Donaldson gave a different explanation. Okay, so and we'll see this is very important in later developments. Right. So the K stability is defined to in this way. So we call XL is K polystable or K stable if the CM weight is non-negative and it's positive, strictly positive for non-trivial test conversions. So for XL with the continuous automorphism group, we use the polystable version. So that requires this CM weight to be strictly positive for non-product test conversions. So in the final case, there are nowadays a very big collection of works. So because the main progress in this case is because we have a very powerful minimal model program, right? So it has been used by many people, including Odaka, Li Xu, Fujita, Liu Xu, and Zhuang. Here just highlight my early result. One was still PhD student. I proved with Chen Xu that for final varieties, special test conversions service for K stability. So this special means that the central fiber we use the still use the final varieties with the mild singularities. And one key ingredient in this work is we discovered that TNCM weight actually has this monotonicity property along the MMP. So if you vary the polarization along the canonical divisor, and if you calculate the derivative of the TNCM weight, surprisingly, it's decreased. So I think this is a very interesting phenomenon about a connection between this K stability and the minimal model program. Of course, this has been developed in much more general and different directions later. One development in this final case is the construction moduli space of K polystable final varieties. First, using analytic methods by myself, Xiaowei Wang, Chen Xu, and then now there's a complete algebraic construction by many people, Bloom Xu, Liu Xu, and Zhuang. And we also know that this projectivity, this moduli space actually is a projective variety. So this depends on, again, showing that TNCM line bundle is positive. It's completed by Xu and Zhuang. Okay, another point of view toward this K stability is by using the so-called non-Archimedean framework. So in this framework, the set of test configurations can be considered as some regular non-Archimedean metrics on non-Archimedean bundles, right? This has been used to reformulate some of the classical results and also give some general framework for dealing with the K stability for general polarizations, for example. Another, I think, interesting result about K stability is that there's a so-called evaluative criterion. So in the final case, this gives a if and only if characterization of K stability. So we can attach to any valuation an invariant, which we call beta invariant. And the final variety is k-stable if and only if for any valuation this beta invariant is positive. So in fact, this beta invariant, the reason why this is true is because partly because that this CM invariant for special test convention actually is equal to some beta invariant for some appropriate valuations. So it's maybe give some explanation why this is true. Okay, so this is a purely algebraic discussion for case stability. Now we want to connect with some analytical objects. So if we have any test convention, actually it gives rise to some so-called geodesic arrays in the space of kinematrics. And this geodesic array is modeled by algebraic singularities. But analytically, it's a solution to some homogeneous complex Monge-Ampere equation on the product of X with a half cylinder. Yeah. I think probably the first work that point out this connection probably is the work of Arezzo and Tian, where they constructed some analytic geodesic arrays, which means that the solution is analytic. So, so later, in more generality, it was constructed by Fong and Sturm, and also a different construction was proposed by Rose with Nystrom. And so this geodesic array consists of potentials in the same cohomology class, and then we can evaluate this K energy and see how it grows along this geodesic array. And now we have this slope formula, which tells us that the slope of this K energy along this geodesic array is given just by the CM weight of the test convention. Yeah. So again, this was proved by Tian. I think okay. So yeah, for sub-geodesic array, proved by Tian, some of the Yongse, and for geodesic array was proved by Xia and myself. Okay, so this is basically the connection between one way to connect the test conversion with this analytical problem. Okay, but to attack this Yao-Tian-Dong's conjecture, we sometimes need to consider not just the smooth scalar potentials, but a more general omega pluri-subharmonic functions with less regularity. So that's why we need to consider some completion of the space of kinematrics. So this was defined by using pluripotential theory by many people, and it's important for studying the variational aspect of this canonical CSE kinematrics. For example, this properties conjecture later was proved actually by using this completion of space of kinematrics. So on the algebraic side or non-Archimedean side, we can also consider some completion. That's why this non-Archimedean framework actually is conceptually quite useful. So there's a way to complete the space of test conversions. And as we said, each test conversion corresponds to a geodesic array modeled on algebraic singularities. So the completion of the space of test conversion can be thought of as the set of algebraically approximable geodesic arrays. So these geodesic arrays are the rays in this H bar that can be approximated by geodesic arrays in finite-dimensional Bergman space. So I think this was also pointed out in Tian's comment to Jake Solomon's talk yesterday. So a priori, there can be quite bad geodesic rays with very bad singularities. However, for the Xiaotian-Donaldson conjecture, actually, we just need to consider this approximable maximal geodesic rays. That is one of the technical results that we can prove. So in some sense, this is a very weak version of this Yao-Tian-Donaldson conjecture. Basically, we are saying that to test the properties of K energy, it's enough to test the slope along this geodesic rays, which can be approximated by finite-dimensional geodesic rays, by these algebraic geodesic rays. But the problem left is that we are not yet able to prove that the left-hand side can be approximated by TNCM weight. So that is the open question. So again, so the Yao-Tian-Donaldson says that it needs a CSK metric if and only for any test conversion, the CM weight is positive. So now the weak version we can prove is that you can choose any element from this completion of test conversion, space of test conversions. And we can define some CM weight associated to any such like a generalized test conversion, if you like, you can call it. And this CM weight for this phi actually has the same expression as in Tian's formula, except now we have to use a line bundle that is not necessarily ample on the total space of degeneration. We require to be big in the sense that it has maximal growth of dimension of holomorphic sections. And also for big line bundles, there's a way to do intersection theory, but it's not the classical intersection, it's called a moving intersection. Yeah. So it has been developed by algebraists. But the good thing is that we have exactly the same formula. Even though we don't have a complete understanding of how to approximate the quantity in this formula. Yeah, that's the so-called regularization conjecture. So the conjecture says that actually we can approximate the formula on the previous page by the CM weight of test conversions, this classical intersection formula used by Tian. So I think this is a reasonable conjecture, and because just on the face it has the same expression, so one would expect to just be able to approximate this moving intersection product by ordinary intersection product. And actually the second term, this L bar to the n+1, this term is indeed can be approximated by the classical intersection product, but the open problem is that for the first term is not quite well understood. So, but I think it should be quite interesting to figure this out, whether it's true or not. And also, actually, there's maybe a local version that is probably also interesting. So this says that if you have any valuation over a point, let's say on the smooth space, and you can look at the ideals in the local ring defined by this valuation space, and there's a invariant called the log discrepancy attached to any valuation, real valuation. This also appeared in previous expression of beta invariant. So this kind of to define it, it's not very difficult, but it kind of a very mysterious environment, which is still, we don't have a good analytic understanding of this environment. So I think a local version of this deregularization conjecture should also be true. That is, this log discrepancy should be the limit of some invariants, first term coefficients of these evaluative ideals as lambda goes to plus infinity. So this is again motivated by the K-stability question. There are other open questions, including the relationship between uniform K-stability, and CM stability. Also, further, we want to have a moduli space of polarized, K-polystable polarized manifolds. So these questions are all open in general, and it's only understood in the final case, due to work of Liu and Xu and Zhang. Okay, I think my time is up, so I will stop here, and happy birthday, Professor Tian. Yeah. By the way, this is a picture actually from several years ago in Tian's birthday, 60th birthday in Sydney. So I just put it here. So these are some of his Chinese students. So, okay, thank you.
Thanks. Any questions? So I have a question. I didn't understand when you talk about one slide of a minimum model program, what do you mean by this weight is decreasing? What does that mean?
Right, so if you have a test configuration, in general, the central fiber can be quite complicated. It can be irreducible. It can have very bad singularities. So in minimum model program, there's a way to modify this test configuration to make it, in some sense, simpler. For example, to make the central fiber irreducible in our case. So that is achieved by doing some variation of this polarization. And for T sufficient small, you still have a polarization, still have an ample line bundle. But when T is big, you would hit some threshold, such as this line bundle stops being ample or semi-ample. Then we have to do some surgery by using MMP. Yeah. So that's what we mean by running this MMP to simplify the test configuration. And along this process, one can show that this CM weight is decreasing. So in the end, we get a special test configuration. So if the original test configuration has negative CM weight, then the special test configuration at the end also has a negative CM weight. And in this way, we show that if the CM weight is positive for any special test configuration, it must be positive for any other test configuration. In this way, it shows it surfaces to test on special test configurations. Yeah.
Thanks. Any questions?
But this change of this variation of ART, this polarization, is almost the same as how the Keller class evolved along the Ricci flow in this since I studied with Song Jian. So this on the other hand, we know the Ricci flow then decrease the K energy, but that has to be a fixed Keller class, and then like cannot be polarized. So in that case, ART is not changing. So is there possible you can lift this inequality? This CM weight is a limiting of K energy. So somehow it's a square here. There are two sides has a monotonicity property. Is there a kind of lifting of this property to the K energy, or kind of a functional, so that the Ricci flow decreases, even Keller class changes? So that might be useful to study this so finite singularity for Keller Ricci flow.
Yeah. So Yeah, exactly. So this is the Kähler class changes on in the same way as in the Kähler-Ritchie flow. Yeah. Because Kähler-Ritchie flow maybe it's also analytical minimal model program. So some sense. So yeah, for this fine time singularity, yeah, I think there's probably a way to formulate some minimization problem to give a description about, for example, the formation of Kähler-Ritchie solitons. Yeah, I mean a special case is this Hamiltonian conjecture. So that is one. The limit is a Kähler-Ritchie soliton, and for the general Kähler-Ritchie flow on general varieties, manifolds, algebraic manifolds, I think that there also should be a way to formulate algebraic formula or algebraic formulation for the formation of a Kähler-Ritchie soliton. I think that is possible. So I mean, I have some like a rough idea of just writing down a minimization problem, but I'm not yet ready to prove that it indeed gives a full description.
Thanks.
I mean, this so for example, Chen class, there's a transgression, so you get Chen-Weil theory, you get so you get forms representing a Chen class. Then you integrate the Chen classes or both Chen class, the transgressions, you get K-energy or these type of functionals. So so this monotonicity, what I mean is whether there is a possibility of so to on a level higher, so on the forms or on the certain functionals, so that we get some more monotonicity for along the Ricci flow. So that might be different. It's not only algebraic. I mean, algebraic. Actually it's very interesting, this monotonicity, but as I said, it's for general Kähler-Ritchie flow, you don't have a monotonicity yet, except the Paramat function. But for K-energy type, we don't have it yet. So, but if you fix the Kähler class, like in the Huaidong-Gauss case, you have monotonicity. In the fellow case, you have monotonicity. In that case, the form in the Kähler class is not changed. So what I mean general, so the Yuan formula is for general polarizations. So I just wondering. So
yeah, I think for this Hamiltonian, the limit in some sense the Kähler-Ritchie soliton is I mean one can use this Paramat's energy to see that the limit should be a Kähler-Ritchie soliton. Algebraically, one can also minimize some functional to detect this Kähler-Ritchie soliton in some sense. Yeah. So I think probably it's also true that one can detect this formation of Kähler-Ritchie soliton. I think that probably there's some conjecture also by Song Jian and me also, and also you that there's a way to describe the fine time singularity and how to form a Kähler-Ritchie soliton. That's what I think probably it's also true.
so also for this your theorem, not the theorem, this norm of phi is kind of is that same, and I guess in the case of fellows, this is just uniform case stability, right? Is that equivalent to uniform case stability?
Yeah, it's kind of uniform case stability. Yeah.
In the fellow case, so then this Chen Yangshi, these people's work can prove can imply this condition is same as K stability. So I guess in general case you don't have that. You need a kind of theorem like what they
Right.
did.
Right. That's why I put the open problem. Yeah.
Mhm.
Relation between
But,
unit and stability.
But this phi, what is normal phi? It's kind of like a weight and height. Bowman had some recent paper on this is a kind of height, but still maybe for Fano manifold. Is normal phi is like kind of height. So
It's
for algebraic case, like say at least I guess is for Bergman type degenerations for degeneration generated by embeddings. That's probably just height, right?
uh okay. Yeah. Maybe it's related, but here we just basically, for example, if this phi is coming from test conversions, it's just kind of normal for test conversion. We look at the weight um of the central fiber, like on the the Hilbert weights on the central fiber, and take this uh the weights and like L2 or L1 weights, and you normalize and you take a limit. So it's kind of the limit of J function along this test convention, along this geodesic ring. So it's probably simpler than that.
I guess it should be equivalent to kind of height.
Yeah. In some sense, it can be expressed using weight, like this Cho weight or something. Yeah, it's really because this this J and like this slope of J functional is related to this Cho weight. This Cho weight is used to define the height of
Yeah, if in terms of chance, these pairs, stability pairs, this if you it's a J functional, it derived J functional. If this normal phi is kind of an asymptotic value of J functional, then maybe you can formulate in terms of these pairs, in terms of this, as you said, in terms of Chow coordinate. And so then in that case, this condition maybe can formulate it as in Chance formulation framework. It's polytope. It's about two polytopes, and one polytope is inside another polytope. If you have a kind of uniform inside another polytope, that's equivalent to probably this condition you have. At least if that is true, then maybe there's a combinatoric formulation of the condition. That might be interesting.
Yeah, I think yeah, in principle one can formulate this condition using this notion of stability for pairs, but I think the problem is that the left hand side, the limit of this slope, the limit slope at infinity, we don't know how to approximate by using fine dimensional quantities, because here this maximal geodesic ray, it's approximated by a sequence of geodesic rays. Basically, you need to put into a sequence of projective embeddings. For each projective embedding, one get a pair, and
Yeah,
I think
I understand that this is a sequence of pairs,
yeah,
a sequence of pairs of polyhedrons. But I
right.
mean, if one is uniform inside of another in this sequence, when the embedding increases, that's probably same as these conditions.
Yeah, it should be true. So and if this uniform control of these two polytopes can be used to imply, because I think for each pair, you get you get also a slope relative this you have, by using this polytope, you calculate the weight difference or something, you get a slope. So you get a sequence of slopes. sequence of slopes. If one can show the sequence of slopes converges to the slope on the left-hand side of this inequality, then it should be true. Yeah. But I think it's not clear how to. Basically, we want to give a description of this left-hand side, this slope, by using approximation of finite dimensional quantities. For each pair, you get a slope, and you want to get a limit of slopes. To say that the limit of these slopes is equal to the left-hand side. I think probably it's reduced to that kind of problem. Thank you. Oh, thank you.
Okay, thanks Tian and Cili for the additional many useful stimulation comments. Any questions, comments, or maybe counterexamples? If not, let's thank Cili again.
Thank you.
So the next talk will be at 10:30.